First, I will introduce myself. Myself, Dr C R Kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today, I am going to discuss about EPR, means Electron Paramagnetic Resonance and Optical Absorption Studies of Iron 3 plus doped ferric oxide. This is iron 3 plus doped Borophosphate Glasses. Today, I am going to discuss about the topic name is EPR and Optical Absorption Studies of Iron 3 plus doped Borophosphate Glasses. So last and previous session was discussed on the EPR and luminescence properties of Mn2 plus doped Borophosphate Glasses. These are the outline of the last section. Topic is introduction and evidence of mixed alkali effect, experimental methods and techniques, results and discussion, conclusion. So today our topic is EPR, means electron paramagnetic resonance and optical absorption studies of iron 3 plus doped borophosphate glasses. The outline of the today talk is introduction of the borophosphate glasses, next experimental methods and techniques of the iron 3 plus doped borophosphate glasses, results and discussion on the borophosphate glasses, conclusion or summary of the EPR and optical absorption studies of iron 3 plus doped borophosphate glasses. So introduction. So general introduction of the present topic is, in recent years, the interest in inorganic glasses containing transition metal ions has grown because these glasses have properties of technological importance in electronic, tunable solid-state lasers and fiber optic communication systems. It is known that sodium borophosphate glasses are of great technological interest. These are the great technological interest because it's the sodium borophosphate glasses. These are mainly technological applications such as electronic applications they are using. At the same time, tunable solid-state lasers, fiber optic communication systems they are using for the sodium borophosphate glasses for the technological application. This is one of the important applications using for the iron 3 plus doped borophosphate glasses. The second one is electrical conductivity and infrared studies on sodium borophosphate glasses have been reported in many investigators. So far they have studied the electrical conductivity and infrared studies on sodium borophosphate, but less studies on the optical absorption studies in iron 3 plus doped borophosphates. That is why these studies provided very informative data on the nature of the work, that is the type and concentration dependence of the variety of boron oxygen arrangements. So in this study, we are mainly focused on the concentration dependence. While increasing the concentration, how EPR and optical absorption studies will be varying. At the same time, boron oxygen arrangement, how it will be structured looks like in the borophosphate glasses, sodium borophosphate glasses. That is we are going to study in this present study. So sodium borophosphate glasses were considered to be an excellent host media for iron 3 plus ions. This is an excellent media for the iron 3 plus transition metal ions, iron ferric oxide, Fe2O3, that is iron 3 plus ions, because of their attractive spectroscopy. So this is mainly highly attractive for the spectroscopic characteristics, that means optical, luminescence and properties of the spectral studies. They are highly useful for the sodium borophosphate glasses. That is why chosen for the present study for the sodium borophosphate glasses. These are the general introduction for the sodium borophosphate glasses. Next, the ionic conductivity of alkali borophosphate glasses has a nonlinear dependence on composition when borate replaces phosphate, and this behavior has been called the mixed glass former effect. So recently, borophosphate glasses have been developed for a variety of applications due to their unique properties such as low dispersion, relatively high refractive indices, etc. compared to the borate and telluride glasses. Mainly, if you are comparing with borate glasses and telluride glasses, the borophosphate glasses having the unique properties. That is, unique properties such as low dispersion value. Is having the low dispersion, at the same time relatively refractive index will be more. So more refractive index value we are getting in the borophosphate glasses. That is why this is one of the unique properties will be exhibit compared to borate and telluride glasses. That is why we are choosing the borophosphate glasses. Next one is presence of phosphorus pentoxide P2O5 extends the ultraviolet region and reduces the infrared transmission. So it will extends the ultraviolet region whenever borate glasses doped with phosphorus pentoxide, that means phosphate P2O5. At that time, it automatically spectral range of the, if you see the absorption spectrometer, you see the UV region will be extended. At the same time, infrared region will transmission will be reduces. That is one of the unique property whenever the presence in the phosphorus pentoxide P2O5 whenever present in the borate glasses. So it will exhibit the extent of the ultraviolet region and they reduce the infrared transmission. It also reduce the chemical resistance of the glasses also. So and also it will reduce the chemical resistance of the glass former. So these are the main introduction for the sodium borophosphate glasses whenever doped with iron 3 plus doped glasses. So now coming to the material selection. The present material selection highlights the fact advantages behind the selection of borophosphate glasses systems for the present study. So, for the present study. In our present study, we have studied on the EPR, electron paramagnetic resonance or electron spin resonance, and optical absorption studies in sodium borophosphate glasses doped with iron 3 plus ions. This is our present topic name is the EPR and optical absorption studies in sodium borophosphate glasses doped with iron 3 plus ions. So first we need to choose the chemical composition doped with iron 3 plus system. So here we are taking the sodium phosphate NaH2PO4, that is 40% of NaH2PO4 we are taking is this is a glass former, and also 60 minus X B2O3, that means boron trioxide, and X is equal impurity, that means dopant iron ferric oxide Fe2O3. So finally we can get sodium borophosphate glasses doped with iron 3 plus. Here X we equal to, here changing the X concentration. So total will be 100 mole percentage. So we are taking 40% of sodium phosphate, 60 minus X of boron trioxide, X mole percentage of iron trioxide. So here varying the X percentage, that means iron content we are varying. At the same time borate concentration reducing from 60 minus X. So X equal to here 5 mole percent, 10 mole, 15 and 20 mole. So X in the mole percentage. So this is the present glass composition. We are choosing the chemical composition, optimized chemical glass composition. So optimized means it should be come total value 100%. So 40 minus 60. That means we are 60 minus X, X is varying. That is 5. 60 minus X means 55. 60 minus 10 means 50. Like that we are to choosing the chemical composition. This is the optimized chemical composition of the iron 3 plus doped borophosphate glasses. Next coming to the experimental technique or methods. So we are preparing the glass sample by using the melt quenching technique. This is the famous and unique technique for the prepare the glass sample. That is melt quenching techniques. So before going to do the melt quenching technique, first we have to take the above mentioned chemicals. So we have to take NaH2PO4 sample, chemicals, and B2O3 boron trioxide sample and iron trioxide sample. The three samples you have to chemical composition you have to take, and that weight should be in the grams of 80 to 25 grams. We have to weigh the by using the optical balance. We can weigh the that chemicals. After weighing the chemicals, we have to pour into the platinum crucible. So platinum crucible is used for the melting purpose. So in that we are pouring the chemicals. So weighed chemicals of 80 or 25 grams of it is a batch composition. We can vary from 80 to 10 grams or 15 grams or 25, not more than 25. In between 88 to 25 grams we have to take, because we are going to measure the optical and characteristic methods. That is why you have to use very less amount only, up to 25 grams only. We are not bulk glass preparation. We are using for the experimental studies purpose only. So you have to use less amount of the chemicals only. So up to maximum 25 grams. So that we are taking the after optical balance chemicals, then we are pour into the platinum crucible. Then after pouring the platinum crucible, we have to keep into the electrical furnace. This is the electrical furnace at the temperature of 1000 degrees centigrade for 30 minutes duration. So this is the melting process. So you have to choose the melting temperature because we are preparing the sodium borophosphate glasses. So we need temperature is melting temperature at 1000 degrees centigrade. 1000 degrees centigrade. Duration time is 30 minutes. Half an hour. Half an hour we have to keep the chemicals at the temperature of 1000 degrees centigrade for half an hour. After melting the glass composition, we have to pour into the preheated brass mold. So preheated brass mold we have to keep in the that melted liquid. So that liquid pour into the preheated brass mold at the temperature of 300 degrees centigrade, because this is, you can say this is annealing temperature. So annealing temperature, this is below the glass transistor TG value, below the TG value. So this would be is less than equal to TG. Suppose TG value of the sodium borophosphate is 350 or 340 degrees centigrade, means we have to choose less than that glass transistor temperature for annealing purpose, because annealing is mainly, what is the use of annealing means, so to avoid the thermal stress and strain, so to avoid the breaking or cracks on the glass sample, that is why we are using for the annealing at 300 degrees centigrade for the prepared sodium borophosphate. After annealing temperature 300 degrees centigrade, we are keeping for 10 hours or 12 hours. After that, it come to the room temperature. We can take the prepared glass sample to polish and cut the samples in small pieces. Then we can do for the different kind of spectroscopic analysis. That means XRD, optical absorption, EPR, and luminescence. Different kind of spectral properties we can study the after preparation of the glass sample. First, initially we need to measure the XRD profile. That means XRD, X-ray diffraction. So by using the X-ray diffraction, we have to confirm this is pure glass sample or crystalline sample. Because if you are getting the broad peaks in the XID profile, so we can say no doubt at all it is a completely exhibit the glass nature. Whenever you are getting sharp peaks, that is due to the crystallization property. So it exhibits the crystalline property. But in our case, in a present class, it shows the broad peaks only. That is why we can say that this is completely glassy nature. So we can use for the further optical measurement studies. So this is the experimental technique and methods for the iron 3 plus dope borophosphate glasses. Next, coming to the experimental technique methods, that means characterization techniques. In our present study, we are doing the two techniques. One is the EPR spectra, other one is optical absorption spectra. In EPR spectra, the electron parabank resonance spectra of the sample we are taken is a Geol FE1X ESR spectrometer. That is company name is Geol from Japan company. This is spectrometer operated in the X band frequency. That is X band. Different kind of X band, Q band, and W band is there. So in our present study, we are using for X band frequency. That is a microwave frequency. Range is 8.8 to 9.6 gigahertz with field modulation is 100 kilohertz. 100 kilohertz. These are the important parameter for the while measuring the EPR spectra. So this is one of the important unique technique to measure the ESR analysis or EPR analysis for the present studied glasses of iron 3 plus dope borophosphate glasses. Next, other technique is absorption, optical absorption spectrometer. So by using the optical absorption, we are using the Flickr spectrometer. That is company name is Lambda 950. The wavelength range from 250 nanometer to 2500 nanometer. We can scan the from UV visible to far infrared region. So we can scan the optical absorption spectra from the 250 nanometer to 2005 nanometer by using the Flickr spectrometer. So these are the calibration techniques for the present study samples. Next, results and discussion. First, we have to results is EPR analysis. So first figure 1 shows the EPR spectra for various iron 3 plus ions in sodium borophosphate glasses at room temperature. So present sample we are studying the at room temperature only. So here X equal 5 mole percent, that means 5 mole percentage of iron 3 plus ions, 10 mole percentage of iron 3 plus ions, 15 mole percent of iron 3 plus ions, 20 mole percent of iron. The different concentration of the iron content. This x-axis is a magnetic field in gas. We are microwave frequency. We are in X band EPR spectrometer. We are fixed the microwave frequency 9.6 gigahertz. We are varying the magnetic field different gases from 0 to 5000 gas. In a y-axis, we are measuring the first order derivative absorption curve. So here you are getting in this from room temperature, that means at room temperature 5 mole percentage to 20 mole percent, we are varying the different concentration of iron 3 plus ions. Here see the, we are getting the two sharp peaks. One is G equal 2.02 and G equal 4.2. These are the Landis splitting factor, spectroscopic Landis splitting factor of the, we are getting this analysis from the EPR spectra only. So at G equal 2.02 and G equal 4.2. Here see the from 5 mole percentage we are getting intense peak at G equal 2.02, at the same time G equal 4.2. And if we increase the concentration of iron 3 plus ions 10 mole percentage, so we are getting this G equal 2.02 is sharp peak will be like broadening. But in the 10 mole percentage intensity is decreased compared to 5 mole percentage. Next again you are increasing 15 mole percentage. Completely 4.2 peak will be disappear and 2.02 peak will be observing with the broad. Next 20 mole percentage also slightly decreasing the broadness. So this is the room temperature EPR spectra with the different concentration of the iron 3 plus ions. So in this study, what information you are getting from the at room temperature EPR spectra? If you see here, this is EPR spectra at room temperature. From figure 1, one can observe that iron 3 plus content is increased beyond the 10 mole percentage. The signal G equal 4.2 begins to disappear. See here, that only G equal 4.2, 5 mole percentage appearing, and 10 mole also it will intensity decreasing, and after 15 mole percent it will be disappear. That means at more than 10 mole percent it will be disappear. That is we are telling here. The signal at G equal 4.2 begins to disappear, and a broad signal G equal 2.02 develops. That means the broadness of the EPR signal at G equal 2.02 will be increasing. That means develops, and G equal 4.2 is decreasing and it disappears at more than 10 mole percentage of iron 3 plus ions. This may be due to the formation of iron pairs or iron clusters. We can say as iron 3 plus clusters. That is a group of iron 3 plus ions pairs by spin-spin interaction containing two or more paramagnetic ions. This is mainly attributed or involved to the mainly due to the spin-spin interaction with iron 3 plus ion to iron 3 plus ion, two or more paramagnetic ions. That means iron 3 plus ion to iron 3 plus ions, this spin-spin interaction. That is why that will be happens at G equal 2.02. It will be increasing the concentration, broadening takes place. At the same time, G equal 4.2 will be intensity will be at a low concentration will be intensity more, and increasing the concentration decreases intensity, and more than 10 mole percent it will be disappear. This is the here like this. That is the information we are getting from the at room temperature EPR spectra analysis. Next coming to the at low temperature EPR spectra. So this figure 2 shows the EPR spectra of 5 mole percent. That means low concentration of 5 mole percentage we are taken in the low concentration because it's getting the good intensity at G equal 4.2, at the same time G equal 2.02 also. That is why you are chosen among the 4 concentration we have selected 5 mole percentage of iron 3 plus ion concentration for the low temperature analysis. So here EPR spectra 5 mole percentage of iron 3 plus ions in sodium borophosphate at different low temperatures. That means from low temperature at room temperature to different low temperature we are studying. So at low temperature analysis EPR spectra we are using the liquid nitrogen. So from 300 degrees Kelvin to 123 Kelvin we are studying for the at low temperature. So if you see this EPR spectra analysis at low temperature G equal 2.0, here getting 3 peaks, 3 Landis splitting factors. That means G equal 2.02 and G equal 4.2, G equal 6.4 also. Here additionally one more peak also you are getting compared to room temperature. You are getting additional peak at G equal 6.4. So these are the low temperature. In this spectra, what information we are getting from the at low temperature ESR or EPR spectra? In the present work, the resonance signal observed at G equal 4.2 are attributed to the isolated iron 3 plus ions in axial symmetry, and the resonance observed at G equal 2.02 is attributed to the formation of iron clusters by spin-spin interaction. This is from the at room temperature. Now this is the at low temperature. So EPR spectra of sodium borophosphate glasses doped with iron 3 plus ions sample were recorded at different temperatures from 123 Kelvin to 295 Kelvin shown in figure 2. This spectra has an intense resonance signal at G equal 2.02 and a weak signal at G equal 4.2 with a solder around G equal 6.4. As the temperature is lowered, the broad solder around the G equal 6.4 brightness. That means this observing in the see here in the low temperature EPR spectra. See the at 5 mole percentage different low temperatures. See at room temperature starting from room temperature to the signal will be increasing this intensity at G equal 2.02. At the same time G equal 4.2. First initially it will be at room temperature, intensity will be less. If you are increasing the low temperature, that means reducing the temperature, intensity will be increasing. At this G equal 6.4, it will be slightly coming from and disappears. So that we are studying here. So the spectrum has an intense resonance signal at G equal 2.02, a vague signal at G equal 4.2 with a solder around G equal 6.4. As the temperature is lowered, the broad solder around G equal 6.4 predominates. This is we are observing from at low temperature EPR spectrum. When the temperature is increased, the intensity of the resonance signal at G equal 2.02 and G equal 4.2 decreases in accordance with Boltzmann distribution law. That means increase with the Boltzmann distribution linearly, it will resonance will be decreases while increasing the temperature. While increasing the temperature, the resonance signal at G equal 2.02 or G equal 4.2 will be systematically reduces. Yeah? That means decreases. That is mainly follow the phenomena of the Boltzmann distribution law. This is the one of the important phenomena while studying the low temperature EPR spectra analysis. These are information we are getting from the at low temperature EPR spectra analysis. Next, coming to the number of spins participating in the resonance. Okay, so in this study we are calculating the number of spins participating in the resonance by using the room temperature EPR spectra. So here we are taking the reference as standard sample and sample. Sample means here iron 3 plus dope. Here sample present sample study is we are using sample is iron 3 plus and a reference or standard. Standard or reference is copper sulfate. That means CuSO4 5H2. These are the reference or sample. So this is a reference sample. This sample is our present study is we are using for iron 3 plus ions. So by using this formula N equal AX tan X squared G standard means here reference sample, X means present study iron 3 plus ions. So by using this formula we are calculating. Here A means area under the absorption. So each and every peak we are getting this peak absorption. Each and every peak first derivative absorption curve we can calculate the how much absorption area is there. We are calculating the area under the absorption curve. That value is here mentioning that is AX or A standard. AX for the sample, A standard for the reference sample. So that is scan means magnetic field corresponding per unit length of the chart. G is gain, PM is modulation field with how much modulation we are using for the analyzing the EPR spectrum analysis. P is the power of the microwave source. How much at the microwave frequency 9.6 gigahertz you are using frequency. At that time, how much power you are using? That value you have to use and you have to calculate the number of spins participating in the resonance. By using this formula, we can calculate the number of spins participating in the resonance EPR spectrum analysis. Next, coming to the figure 3 shows the concentration dependence of line width for the resonance signal at G equal 2.02 in sodium borophosphate glass samples. So here in this graph shows the concentration versus line width. So we are calculating each and every line width at the presence of resonance signal at G equal 2.02. So in that we are present at 5 mole percent concentration that line width value gas equal around 400. Next increasing at 10 mole percentage of line width will be increasing. Again 15 mole increase. That means linearly increases by concentration increases, line width also increases. That is mainly due to the ESC. Figure 3 shows the concentration depends of line width for G equal 2.02 absorption line of sodium borophosphate glasses with different concentrations. Here the line width delta X, that is line width that is symbol is delta X, is increases with increasing the iron oxide. While increasing the iron content, line width also linearly increases. It can be attributed to the process by which iron enters into the vitreous matrix, that either iron 3 plus ions, Fe2 plus ions. So whenever the in sodium borophosphate glasses, whenever iron 3 plus ions enters into the vitreous glass matrix, like this structure will be happens because of the concentration varying. At the time line width will be linearly increases. That is the we are studying for the concentration dependence line width of the EPR resonance signals from the sodium borophosphate gas. Now coming to the figure 4 and figure 5 shows the a plot for log n versus 1 by T temperature. Log n versus we are calculating the number of spin oscillations in the EPR spectra, that is log n versus 1 by T. At the same time, paramagnetic susceptibility with temperature. In figure 5 shows the paramagnetic susceptibility with temperature. From in figure 4 and figure 5, we are calculating the in figure 4 we are calculating the by using the number of spins, we are calculating the activation energy. That is in from present study in sodium borophosphate glasses by using this analysis log n versus 1 by T. So we are studying log n equal after linear fit, we have to fit the equation by using the based on the our number of spin oscillations in the resonance signal. That way we have to calculate in the activation energy of the present iron 3 plus dope sodium borophosphate glasses. In that case, activation energy we are getting is 0.01 electron volt. Next, coming to the in figure 5 shows the temperature versus susceptibility 1 by psi into 10 power of 3 meter cube per kilogram. So in this study, we are studying the susceptibility by using this formula Ng square beta square J equal J plus 1. Here N is the number of spins, G is Landau spectroscopic splitting factor, B is the Bohr magnet, G is the quantum number of the iron 3 plus ions, Kb means Boltzmann constant, C is absolute temperature, T. So here J value will be in iron 3 plus ions 5 by 2. We are using J value is 5 by 2. Bohr magnet value is constant value. G is G equal 2.02. N is the number of spins previously we calculated by using formula. That we are using in this formula, we can calculate the susceptibility. By using temperature of 1 by psi, we can calculate the Curie constant and also paramagnetic Curie temperature. We are going to calculate it by using the figure 5 data. So here Curie constant C equal 650 into 10 power. By using this linear fit, we can calculate this value. That value C equal 650 into 10 power of minus 3 EMU per mole, and paramagnetic Curie temperature theta P equal 1.8 Kelvin. So from figure 5, we have to calculate the Curie constant and paramagnetic Curie temperature. In from figure 4, we can calculate the activation energy of the iron 3 plus dope sodium borophosphate glasses. So these are from these two figures we can calculate this analysis, these parameters, activation energy and paramagnetic Curie temperature. Next, coming to the last studies for the optical absorption spectra of the iron 3 plus dope sodium borophosphate glasses. In this optical absorption, we are study the wavelength versus optical density or optical absorption. Here see the x-axis wavelength and optical density in units. This is varying the wavelength. Here see the A, B. If higher wavelength, see A, B, C, D. These are the absorption peak from the ground state to different kind of excited states. So from this graph, we can calculate the what is the information we are getting from this figure means the optical absorption spectra of 10 mole percentage of iron 3 plus ions in the sodium borophosphate sample at room temperature is shown in figure 6. This spectrum exhibits the 4 bands centered at first value 22,990 centimeter, that is 435 nanometer first. So 435 nanometer here A, that is a 435 nanometer, that energy will source the 22,990 centimeters. The second peak we are observing at 394 nanometer here, B value. A, B, C, D, 4 absorption peaks we are observed. So second one is B value is we are getting 25,380 centimeter, that wavelength is 394 nanometers. The third one C value, that means absorption of the C value is 26,560 centimeters of energy, that wavelength is 376 nanometer. Last one D value is 27,780 centimeters of energy, we are getting wavelength is 360 nanometers. So these bands are denoted as A, B, C, D respectively. So by this observation, the observed band positions are comparable with those found for many ores containing iron ions. Whenever iron ions present in the different kind of host glasses, we can observe this kind of poor absorption peaks. That is mainly due to the indicators of iron ions present in the trivalent state with a distorted octahedral symmetry. So whenever iron triplet ions doped into the different kind of host materials, it exhibits these kind of poor absorption bands from ground state to different excited states we are observing. That is mainly due to the presence of trivalent iron triplet ions with the distorted octahedral symmetry. That we can confirm by using the optical absorption spectrometer. We can confirm the iron triplet ions shows the trivalent state as well as distorted octahedral symmetry. So from optical absorption spectra, you can get this information from the optical absorption spectrometer. Using, you have to calculate the optical absorption spectra. In that one, iron triplet doped borophosphate glasses exhibit four important absorption bands. That is exhibits the mainly due to the iron triplet ions content with disordered octahedral symmetry. Next, coming to the from optical absorption spectra only, we can calculate the crystal field parameters also by using the optical absorption. This optical absorption bands, by using the four absorption bands, we can calculate the crystal field parameters and Raka parameters. So from table 1 shows the observed and calculated energies of iron triplet ions in sodium borophosphate glasses doped with iron triplet ions at room temperature. We can calculate the dq is the crystal field parameter dq. So by using the observed bands, these are the A, B, C, D. We are observed iron triplets ions doped within sodium borophosphate glass. We are observed four bands from ground state 6 and 6 A1Gs to different kind of excited states. First one is portrait T2G G value 435 nanometer wavelength. Energy is 22,000 centimeter. So these are from optical absorption bands only. Where this values only we are here note down here. This is from ground state to different excited states. These are the energy level transitions from ground state to excited state. Transition from the ground state 6 set A1Gs to different excited state of iron triplet ions. So we are getting four absorption bands 435 nanometer, 394, 376, 360 nanometers by wavelength, high wavelength to lower wavelength. So low energy to higher energy. So these are calculated wave number by using the Tanabe-Sugano diagram. This is by using the optical absorption spectrometer comparing with Tanabe-Sugano diagram. The crystal field parameter dq value we are getting by using the Tanabe-Sugano diagram. We can calculate the crystal field parameter dq equal 900 centimeter inverse and Raka inter-electronic repulsion parameter. This is the Raka interaction repulsion parameter for iron triplet ions. That value B and C value we are getting by using this observation data only. We are calculating by using the Tanabe-Sugano diagram. We are calculating the three important parameters. One is dq, that is a crystal field parameter dq value 900 centimeter inverse, and the Raka interaction parameter is two parameters, that is the B and C. B value we are getting 760 centimeter inverse of energy. C value is 3400 centimeters energy of Raka parameter we are calculating by using the optical absorption spectrometer. These are we are getting the information from the optical absorption spectrometer while doping of iron triplet dope sodium borophosphate. Next, coming to the finally concluded and summary of the present study is the EPR spectra of all the investigated sample exhibit two resonance signals at G equal 4.2 and G equal 2.02 at room temperature. The resonance signal at G equal 4.2 has been attributed to isolated iron triplet ions in a rhombic symmetry site. This is due to the at G equal 4.2. Whenever you getting G equal 4.2, is mainly due to the isolated iron triplet ions in rhombic symmetry site. Whereas the resonance signal at G equal 2.202 is due to the iron triplet ions coupled by exchange interaction in a distorted octahedral environment. So these are the mainly present by using the EPR spectral analysis at room temperature. We are getting this site of symmetry we are observing in the EPR analysis. Then second one is at a low temperature EPR analysis, we are getting the additionally we are getting one more signal is at a G equal 6.4 is also observed. It has been assigned to be isolated iron triplicine rhombic symmetry site. The line width of the line widths are found to be independent of temperature. The intensity of the resonance signals decreases with increase in the temperature. It accordance with the Boltzmann distribution law. So this information we are getting from the at room temperature ESR spectra as well as at low temperature EPR spectra ESR spectra analysis. Next, coming to the last study is optical absorption studies. From optical absorption spectrum of sodium borophosphate glasses exhibit 4 characteristics of iron triplet ions in an octahedral symmetry. This shows the octahedral symmetry from the optical absorption spectrometer. So in this study, we can calculate the different kind of crystal field parameters and the Raka interelectronic repulsion parameters also. That DQ we are getting 900 centimeter inverse and the B equal to 760 centimeter inverse and the C equal to 3040 centimeter inverse. We are getting these values from using the optical absorption spectrometer. These are the summary or conclusion of the present study on EPR and optical absorption studies of iron triplet doped borophosphate glasses. Next, these are the references we are getting from the EPR and optical absorption studies of iron triplet doped glasses. In this work, mainly presented in this paper. This is one of the myself only, my paper only published in the year of 2010 in the Journal of Physics and Chemical Studies. Journal of Physics and Chemistry Solids. So this is the one of the important paper. This is published in the present study EPR and optical absorption studies of iron triplet doped borophosphate glasses. So these are the cited different references. By using this reference, Dhanaway-Sugana diagram, by using this reference only, we are calculating the crystal field parameters, that is a crystal parameter DQ and a Raka interelectronic repulsion parameter B and C. These are the citations of the present study paper. Next, to be continued in the next section. Thank you once again.
Like, share and subscribe. Hit the bell icon for more updates.